We are going to learn a little bit of fundamentals, right, contacts to 2D material, because at the end of the day, when you make any device, right, you have a material, you have to connect it to the external world, right, and the connection is really the metals that you put on top of this material, right. So therefore, contacts to 2D material is one of the key. Unless and until you can make a good contact to the material, you cannot really get a high performing devices, and it is true for electronic devices, optoelectronic devices, neuromorphic devices, memory devices, right, anything that you kind of fabricate. Okay. So now let us see in the context of transistors that we were talking about in the first lecture, why are contacts important, right. So we go back to this transistor structure, very basic, source and drain, and the source and drain, as I told you, are the metals, right. That is where you are connecting the 2D material to the external world, and then you apply voltage in order to enable current flow through this material. So now when you have a structure like this, then there are like generally three resistances. Okay, one is the resistance of the channel, and the other are the resistances at this metal 2D interface, because the electrons or the holes have to come from the drain or the source and get into the 2D material, and there they will face some resistance. Okay, and that is the contact resistance, right. So this is kind of denoted by RC, and RCH is your channel resistance, right. Clear this part? So now your channel total resistance of the device is therefore not just the channel resistance, but also the resistance offered by the contact. So the total resistance is this. So whatever current you will get will depend upon the total resistance, not just the channel resistance, right. The channel may not have any resistance, it could be completely ballistic, but then you will still have contact resistances, right. So therefore contact resistance is actually very important, because it plays an important role in the total resistance. Now the channel resistance, we know what happens. This is simply following the Ohm's law. If you make the channel very small, the channel resistance will be small. You see, it kind of scales linearly. If you make the channel very wide, right, then you will get more current, because you have a wider channel. Therefore the channel resistance is inversely proportional to the channel width. And then the RSH is the sheet resistance, right. So this is almost very similar to resistivity, but because it is a nano sheet, there is no defined thickness, right. So we kind of club those two things, the resistivity and the thickness, together into this quantity called the sheet resistance, right. And the sheet resistance is a property of the material, and the rest are all geometric factor, because this is something you are designing. You have full control over what channel length of the device will be, what is the width of the device will be. So these are design knobs, while RSH is a fundamental property of the material that you are using. So if you use 2D material versus silicon versus germanium, what is going to change is your RSH, because that is the fundamental material property, and the rest is design. So this is the channel resistance. Now if I wanted to plot the channel resistance as a function of the channel length, then I will get this linear line, right. You can see over here, right, as the channel length becomes smaller, the RCH becomes smaller, and what will happen when LCH is 0? Channel resistance will be 0. But then you see the total resistance is still not 0, right. Why? Because you have a finite contact resistance, correct. So now you see that when my device is very long, right, my contact resistance does not play an important role, because my channel resistance is very large, right. While when I go to very short channel device, your 2RC or the contact resistance becomes dominant. Make sense, right. So therefore for short channel devices, contact resistance is even more important, right, for scale devices or scale transistors, and we are talking about transistors of channel length 10 nanometer, 20 nanometer. So there the contact resistance becomes very important, because if the contact resistance and the intercept is the contact resistance, right, that is your 2RC. If I have a higher contact resistance, right, then my entire curve will shift, right. So that will increase the total resistance of the device. And if my contact resistance is lower, if I can ultimately make the contact resistance 0, which is never possible, right, fundamentally, then I will get a channel resistance to be almost 0, total resistance to be 0, if I could really mitigate the contact resistance problem. So therefore contact resistance minimization is one of the key towards getting high performance devices, because lower the resistance, more is the current, and more is the current, higher is the speed, and better is your transistor, right. So this part is clear. So two take home messages, right. Contact resistance dominates at the shorter channel length devices, correct. That is one take home message, and the second is if we reduce the lower if we reduce the contact resistance, I will get better performance. Right, two things clear. So now the question is the contact resistance. So I have a two device shown over here, right? This is actually a device that we fabricate, and you see I am looking this device from the top, right? So here is your source, here is your drain, and then this is the channel. You see, this is a very small channel length device, right? And here is another device where the channel length is very similar, okay, and but the contacts are also very small, right? Do you see the difference between the two? Which one do you think is going to be a better device? Second one is a better device. Why? Because the device itself is very small, right? Because there is no point of making the channel shorter and keeping the contact bigger, because then I have not reduced the footprint of a single device, right? When we talk about Moore's law, putting more devices on a single chip, not only I have to reduce the channel length, but also the contact length, right? So now, having said that, so we have learned that, okay, if I reduce the channel length, the channel resistance becomes smaller. What happens if I make my contact length smaller? Will the contact resistance also go down? Because ultimately we want to have a lower contact resistance, correct? So isn't it good not to have any contacts, because the contact length is 0, right? You have to have a contact, right? And the contact has to be the short. So shorter contacts, what do you think? Is it going to give me lower contact resistance or higher contact resistance? We learned that a shorter channel gives me smaller resistance, Ohm's law. Does the same thing apply for the contacts? If it were, then there is no problem, our life is easy. It matters on that, but irrespective of the metal, fundamentally, right, when I make the contacts very small, right, so scale devices must have scaled contacts, that we established, right? But when we make the contacts very small, you see there is a very interesting dependence of the contact resistance on the contact length, right? It is a more complex dependence. We are not going to derive this formula, but I am going to write it in the board so that you understand that my contact resistance this is not working. Just bring another one. Can you try, some of you try to draw for me the functional dependence of RC on LC. Why don't you guys try this, right? In the meantime, it's a Court hyperbolic dependence. First of all, you have to remember, what a Court hyperbolic dependence means, right? So let's see how many of you remember that. Okay, so we are trying to plot RC as a function of LC, right? And noting that the mathematical formula for RC is some constant RC0 cot hyperbolic LC by LT, okay, and LT is a constant. Can you help me in drawing RC versus LC? Anybody knows what is cot of hyperbolic x? Let's start there. Very good. E to the power x? Yes. Very good. Okay. So now, generally, when you try to draw a functional dependence of a curve, right, this is very difficult to draw. We can do that, okay. So what you want to do is 1 minus e to the power minus 2x, right? Good, no problem, all good. And in this case, x is, right, and this is a constant, so I don't really care, right? So now, drawing a curve, okay, what is your approach of drawing a curve. This kind of question used to be ISI questions, I remember. Indian Statistical Institute, Viva, if you go for those interviews, they will ask this kind of questions. Yes? Okay, okay, let's see. So what happens if x is actually very large? I don't think this, this is it to the, yeah, that's correct, okay, let's see. So what happens at x equal to 0? It's the other way around. This is not correct. This is cot. What you have shown is a tan. When x is 0, it asymptotically goes to infinite, right? And what about when x is very large? When x is very large, it will approach 1, correct? So, can we now draw? So, for very large x, it is a constant, and then it diverges. See? So, what is the problem here from this curve that it raises any problem? That when my contact length becomes small, my contact resistance becomes very large. This is exactly in contrary to what happens to the channel. I make the channel small, the channel resistance becomes smaller. I make the contact small, contact resistance increases, while my objective is to reduce the contact resistance, right? And for a scale device, there is no rescue. I have to scale my contact resistance, right? Therefore, if I now wanted to plot the total resistance, you see the channel resistance goes down to 0 as my length of the device becomes smaller, but contact resistance becomes large. The total resistance is a non-monotonic trend, correct? So, it goes down, but this is where we are interested. Today, when we are making nanoscale devices, right, we are not in this regime where everything is nice and clean, I reduce my device size, I get better performance. Now, if I make the device too small, my contacts becomes dominant and it dominates over everything, correct? So, you see the importance of reducing or understanding the contact for nanoscale devices. Make sense? This is just to establish that contacts are way more critical than even what channel material. This is true for any channel material. Does not matter with this 2D silicon, right? So, therefore, contacts to any material plays an important role for nanoscale devices. Okay, I have the next slide. Yeah, that's the next slide that I am coming to. Okay, now I am going to give you two scenarios. Before I go to the next slide, I am going to ask you this question. This is not very good, I know. Maybe I will go that side. Huh? That's fine. So, I am going to give you two scenarios. Okay, so we are going to look into near the contact. Okay, so we are going to focus on one of the contacts. Okay, and see how the carrier injection is going to take place. So, this is two scenarios. One is this is your contact and this is your 2D channel. Okay, we are not caring about this part. We are only focusing on the source and the 2D channel. Okay. One instance is, because the electrons has to come from the source, which is metal, which is a lot of electrons, into the 2D channel. One scenario is the electrons come and go, right, throughout the entire contact. The other scenario is the electrons go like this. The difference is the electrons only come into the 2D material all over the contact, or they come at the very edge. Which one do you think is more viable, or which one do you think is actually happening in your devices? Who all thinks is the first one? Raise your hand. Let me see. Vote. Let's vote. How many? A lot of people think it is the first one. Raise your hand very high. Come on. This is morning. Wake up from the sleep. Okay. Raise your hand. Okay. And then who all thinks it is the second one? Very less. Only you think it is this one. Okay. So, democratically, if we vote, this wins, right? Unfortunately, this is not politics. This is science, right? So, this is the one that is going to happen. Now, do you know why? No, this is a metal, right? This is a semiconductor. Which one has more resistance, a metal or a semiconductor? A semiconductor, correct? Now let's think about, you have to go from here to the Kumbh Mela. Okay, you take the straight road which is extremely crowded, and there is an alternative route, right, which is like a highway which takes you far, and then only you have to kind of go near the Sangam, a little bit of walking. Which one will you choose? The second option, right? So why is it not true for this, the electrons? This is a more resistive path, and this is a less resistive path, right? So this is the Sangam, correct? So you will always remain in a very uncrowded or place. Before you go near the Sangam, you get into the 2D material. You see that, right? So this is something that happens in our devices as well, and this phenomena is called something like current crowding. You see, it's literally crowding, but the crowding happens near Sangam. Make sense? Okay. Now the question is, why does, and you see this length is LT, that term over there in the denominator, right, is LT. Okay. So now what happens if your contact is much bigger than LT? If your contact is much bigger than LT, I don't care, because every time the rest of the length doesn't matter, but the contact resistance will not change, because carriers are going to cross over to the channel in that LT, right? No problem. But now if your contact becomes smaller than LT, if the contact becomes smaller than LT, right, then you run into a problem. Correct, you see? Did you see that understanding is clear here? So that's why this asymptotic plot, this point is your LT, right? Because what did we determine? That if, remember this expression, e to the power x plus e to the power minus x, right? And we said that, okay, we also did this, right? And we said x has to be much, much greater than 1 in order for us to be in this regime, right? Only when x is very small, right, x is less than 1, I start diverging. And what was x? Correct? So whenever LC becomes smaller than LT, right, because now it becomes so much more difficult, you can think about it, right? If it's a narrow alley and you have to get into the Kumbh Mela, think about how long will you take to get into the Sangam. While if it's a wide path, right, no resistance, you can easily go. Literally that's what it is. Electrons are trying for Amrit as well, which is in 2D materials, right? Make sense? So this is a fundamental problem with contacts when you are trying to transfer these electrons from the metal into the semiconductor, right? Clear this part, right? So we can see at the end of the day, we need to engineer. So this is our task. We need to engineer the metal 2D contact such that RC is low for scaled contacts. And what is the target number? This is the target number specified by the IRDF, the International Roadmap for Devices and Semiconductors. Okay, so this is how all the semiconductor industries like Intel, TSMC, Samsung follows this roadmap. Okay, and the roadmap specifies that RC has to be below this number. Okay, and you see here the unit is actually not ohm. This is something, a question you should ask me, why the unit of resistance ohm micrometer, right? I mean the unit of resistance is ohm. Why is it ohm micrometer? So if you go back to this equation, you see that both RCH become smaller with the width of the channel, so do the contact resistance. which means that if I make my channel wider and wider, my resistance will anyways go down. That's not a rocket science. You take that thing out and you normalize it to the width. Make sense? So you just multiply RC with WCH and also RC with WCH. So the unit becomes ohm meter or ohm micrometer. Because WCH is not fundamental. I know that if I make my road wider, I will be able to get more people into Sangam, right? That there is no rocket science with that. So what is more fundamental is what happens per unit width, and that is something we have to minimize. Make sense? Get it right? This part is clear? Okay. So we know now our target for the contact resistance. So now let's dig into one thing, is that how in an experiment we extract the contact resistance, right? So experimentally it's very simple. You make a device with same contact length but different channel lengths, right? This is what you can easily lithographically design, and then you can go and measure the device characteristics and plot it. So these are real experimental data that I was showing, and from that you can extract the RC, contact resistance. So experimentally you design this kind of structure. This is called the transmission line model, and based on that you can extract the contact resistance, right? Because at the end of the day, I mean, you can do some theoretical calculation, but until and unless you go and actually do the experiment, you will not be able to evaluate the contact resistance, right? So this is a structure specifically designed for understanding the contact. Okay. And then you have to design the same structure, but now with different contact lengths, because you see both are important for scale devices. So you do the same experiment now with different contact length as well. So that will give you dependence of RC on LC, right? This is what we were talking about, right? And both information are going to be important. Okay. Now let's switch the gear and let's ask this question: fundamentally, how low the contact resistance can be? Okay, we forget about this, so there was this term RC0 in the beginning, you see. So we understand that, okay, there is a certain length scale dependence, right? As I make it smaller, it is going to be higher. We cannot rescue from that. But then there is this prefactor RC0. So the only way for me to reduce the contact resistance is to reduce that RC0, because I cannot get rid of this functional dependence. Agreed, right? So we have to reduce that RC0, and we have to therefore understand what determines RC0. Correct? So now if I go to RC0, this is the expression for RC0. Again, we will not be deriving this expression, okay? And for an ohmic contact, metal semiconductor contacts are mostly Schottky barrier contact, but for ohmic contact, the least resistance that I can have is this. This is the best, okay? It has some fundamental quantities: H, Planck's constant, Q is the electronic charge. I can't change any of these. There is this quantity alpha, which is also like square root of pi by 2. I cannot change it. Right? You see, I am pretty limited. The only thing that is left behind is the carrier concentration in my channel, right? That is N2D. And what does it depend upon? You see, it depends upon, in a transistor, two things, right? One is the gate voltage that I am applying, because by applying gate, I am actually changing the conductance of the channel, and when I am changing the conductance, it is literally changing the amount of charge in the channel, right? Which depends upon your oxide capacitance and your threshold voltage, and this is the formula for N2D. Or you can alternatively do it by doping. If you dope your channel, right, then also you can get different N2D, right? This is carrier concentration. Carrier concentration you can change either by doping it, like for silicon we dope it with phosphorus, arsenic, boron, right? Or you can do it by applying gate bias electrostatically, right, which happens in a transistor, right? And you see that you want to have a very large N2D. Make sense? That is only way to reduce contact resistance. Higher carrier concentration, which means I am targeting really degenerate doping of the channel underneath the contact to reduce the contact resistance, right? So here is a plot. You see that as N2D increases, right, this is the line. Forget about these are all experimental results we will talk about later, but this is the formula for the RC0, correct. And remember what was our target? Target was 50, right. See, the unit is still in ohm micrometer, so we have to achieve 50. So this is like 100, right, over there it is 100, this is kind of 100, right. See, this is 100, so 100 you can achieve over here, that is the quantum limit, you cannot be less than this. This is determined by quantum mechanics, thermodynamics, whatever it is, that is the fundamental limit, right. And you can see that yes, in principle we can actually get down to even like this is 10, right, and we have to be somewhere around 50 possible if we can get to very high carrier concentration in the 2D channel. So therefore, we can meet the IRDS roadmap for a metal 2D contact, right. So no limitation fundamentally, and then these are all the experimental results so far, including some of our own is also there, okay. And you can see that 10 to the power 5 were very early days, okay. These are nickel MOS2 contact, reference 5, most likely one of our papers are there. So early days contact resistance were very large, and see what the 2D community has done over the years to bring down the contact resistance. We are almost at a very hitting distance, you see, like 200. There have been results also talking about almost like 100 ohm micrometer, right. So it is there, right, but it took like 10 years to get to this point, right, of reducing the contact resistance. Okay, okay, so now let's understand a little bit better. So this is all for a ohmic contact, but metal 2D contacts are far from being an ohmic contact. Okay, so we will start talking a little bit about metal semiconductor contact and what does it mean to be ohmic versus Schottky barrier. Okay, this is going back to again a very basic drawing board. So now when you have a metal, metals only have Fermi level, and therefore it is determined by a work function which is phi m. And then you have a semiconductor which has a conduction band, valence band, and based on the doping I have a Fermi level. This is what type of semiconductor based on the Fermi level? This is n type or a p type? This is the n type semiconductor, right. So it has an electron affinity which is given by that chi, that this quantity over here, right, and then it also has a work function which is generally how far is the Fermi level from the vacuum level. So this is when the metal and semiconductor are far away, right. If you bring them close to each other and make this metal semiconductor junction, can somebody draw for me the band diagram? You want to draw? Come to the board, draw, right. You guys know how to draw band diagrams? Okay, be careful, there are a lot of wires here. Okay, yes, yes, you use this one. We have this one, Lucky, this. No. Okay, let me first, anybody else who knows how to draw a band diagram? There are some rules. Okay, there are some basic rules. There are two rules that you have to follow in order to draw a band diagram. Okay, I mean it is not about memorizing. You never memorize how a band diagram looks like. Okay, anybody else who knows how to draw a band diagram? Yeah, I mean when you bring them together, there is a junction. P-N junction, right? You have a P-type material, N-type material, you put them together, there is a metallurgical junction that forms, how the band diagram of a P-N junction looks like. Now we are putting a metal on top of a 2D material. In order to understand metal 2D contact, first thing we should understand is how is the band structure, right? Okay, anyone else? Okay, this is very basic, so we need to know that. Okay, so let me try to wipe this. Okay, so there are two basic rules. Okay, so what I have drawn is, here is the metal, right? So this is the vacuum level, phi m, and then we have the semiconductor. In this case, you notice that the work function of the metal is bigger than the work function of the semiconductor. Okay. This is phi s, this is your electron affinity. Okay. This is what we have to start with. Rule number 1, when you bring and make a metallurgical junction, the Fermi level is same throughout, okay, because you are in equilibrium. So Fermi level is same throughout. So first thing I will draw is the Fermi level. Remember, this is the Fermi level for the metal, this is the Fermi level for the semiconductor. Once you bring them together, they cannot be different. Okay, that is rule number 1. Okay, so that is done. So therefore, the metal is somewhere here. Correct? Far away from the junction, far away from the junction, the semiconductor remains semiconductor. There is nothing that the metal can influence it. Right? So far away from the junction, if I have to draw, right? You see, this is where my conduction band has to be. This is where my valence band has to be. Far away. Okay? Because it's an n-type material. Now the junction. That's rule number 3. Rule number 3 is the difference from the vacuum level of these two has to be maintained at the junction. Right? How can I do that? How can I do that? I can only do that if the band is somewhere over here, and let's say this is a vacuum level, so that this distance is chi, this distance is phi m. I told you the distance has to be at the junction, they need to maintain their relative position with respect to the vacuum level. Correct? So therefore, there will be a barrier over here. Right? Got it? Right? So at the junction, the relative position of the conduction band and the Fermi level for the metal has to be the same with respect to the vacuum level. So this is the vacuum level. So therefore, the conduction band of the semiconductor should be at a distance of chi. Right? This is where it is, while this is phi m, because we are doing by assuming this as a reference level. Got it? Right? So now here is the conduction level at the junction, and here is the conduction band far away from the junction. So there is no other option but the bands to bend. Therefore, there will be band bending, because the band gap cannot change of the material, this still remains the same. This is how the junction will look like. Right? Now you see, there is a problem in this junction, because we want the electrons from here to come into the channel, right? But will they be able to come? Because there is a barrier, potential barrier, correct? And this is what we call the Schottky barrier, right? So therefore, the expression that we derive for the contact resistance, true for ohmic contacts, not true for this, because now the carriers cannot easily come in. So contact resistance is going to increase or decrease? It's going to increase, right? If you put up a wall in front of your sangam, people have to jump over. It will slow them down even more, right? Make sense? So therefore, Schottky barrier is something we also have to care about. We have to make the contacts ohmic in order to get to those numbers that we are talking about, in addition to the other things. So this is what is going to happen. I told you. Make sense? The Schottky barrier. So now, if I ask you that, okay, our objective would be to make this barrier 0. If there is no barrier, then I am again back to my ohmic contact. If I have to make this barrier height 0, what kind of a metal should I choose? Should I choose a metal with a large work function or a small work function? Small work function, because then my phi m minus chi could be 0. Right? So if I have a material which has a smaller work function, okay, in this case Can some of you try to draw the band diagram? Now I have already shown you, right, the rules, rule number 1, 2, 3. Any brave soul here who wants to try drawing the band diagram for this? Yeah, all of you can try in your, try it in your paper, and then you can try in the board. Yeah, first you draw it on the copy. I can see it in your copy, and then if it is correct, I will ask you to come and draw it over the board. Take 2 to 3 minutes, no problem. Correct, to some extent, almost there, almost correct, almost correct. Yes, to some extent. There is still one small mistake. So do follow the rules. Do follow the rules for this drawing. Then you will get the correct picture. Rule number 1: Fermi level is the same throughout. Right? That is rule number 1. Rule number 2: far away from the junction, the semiconductor remains the semiconductor. So the relative position of the conduction, Fermi level, and valence band will remain the same. And then at the junction, the relative position of the conduction band of the semiconductor and the Fermi level of the metal should remain the same with respect to the vacuum level. Yes, let me see. Yeah, correct. You want to draw? It is, but there is some, you will see. Okay, you can draw it. You can draw it. And explain and draw. You know, how did you do it? Like the 3 rules. You draw first? Yeah, fine, fine, fine. Yeah. Correct. Very good. Yes. Difference is there. I can clearly see the phi m is kind of smaller and your phi s is larger. No, I think you want to put it even higher. Okay, yes, higher. Yes, you have to put it even higher. If you want, you can put it even higher. But this is fine. This is fine. So now you can, yeah. Fermi level is same throughout. Correct. So you draw the Fermi level first. Very good. Yes. Then you draw the metal. No, you draw the metal assuming that that is my reference. Okay. So you draw the metal next. Because metal is at the Fermi level, right? So that is my Fermi level. Correct. Done. Yes. Very good. Right. Far away from the semiconductor, it will remain exactly the same. Very good. Right. Right. At the junction. Right. Something has, no, that is not the rule. That is not, the rule is that this position and this position has to relatively stay the same. Correct? Yeah. I think you have to, I think your drawing is not exactly correct because you see my phi m is even lesser than chi. Right? So that has to be the case. In this drawing, this is not yet. So I will just push it a little bit up higher. Right? Because that's how it is drawn over there. You see phi m. This is phi m, right? So now you see if this is phi m, this is my chi, right? So if phi m is stuck here, chi has to be bigger, right? So your this point, your EC, no. So I think you draw it correct. EC is now here. Make sense? EC has to be there. So your Fermi level remains the same. So now it will bend downwards. This will also bend downward. But the only the problem in your drawing is that you see the Fermi level was not there. So your Fermi level is now, it is here. Make sense? You see your conduction band actually crosses over your Fermi level, right? No, your Fermi level is still below the conduction. Yeah, that's what I am saying. That's a very critical thing, because when your Fermi level moves into the conduction band, what does it mean about the semiconductor? It is degenerately doped, correct? And that is why it becomes an ohmic contact. Make sense? Okay. Bending will be not only more, but you see there is also a crossover. It's just not the bending. So if you follow the three simple rules, you will get to the band structure. That's why I'm saying you never remember how that, oh, it has to bend in one direction versus the other direction. That will confuse you. Three basic rules, and you can draw the band structure of anything on this planet. Okay, these three basic rules. Okay, good. Yeah. Yeah, maybe one person repeat the three rules. Good. Second rule. No. And the third rule. Somebody else tell me the third rule. That is the most important rule. Okay, first two rules are easy rules. Relative position of the Fermi level, I mean the work function of the metal and the electron affinity has to be the same with respect to the vacuum level. Chi, electron affinity. Good. Hopefully you remember these three rules. Okay, then you will not struggle in drawing band diagram ever. Okay. So this is what happens for the N type, and then what we say is that the first one is a Schottky contact for an N type FET, and the second one is an ohmic contact for an N type FET. Because remember, we have to get to an ohmic contact, only then all those discussions that we have earlier today is valid, right? So therefore, for an N type material, you will choose a metal with low work function. Make sense? Okay, what happens if I change it to the P type material? Okay. Okay. Another task. Why don't you again, let's see. Okay, we will have practice. So what about the band diagram for this? Now you see what is the material here, the semiconductor is P type, because the Fermi level is close to the valence band. Now let's try it one more time. So by the end of the day today, you will be experts in drawing band diagrams. That is one thing you will definitely learn out of this GAN course. Same rules, okay, it doesn't matter whether it is N, P, basic rules are the same. Let me try to clean up the board in the meantime. भैया आप मुझे मेरा क्लीनिंग करता हुआ पिक्चर मत लीजिए, इन लोगों का लीजिए अभी. He has moved the camera towards me when I am cleaning. Yes. Let me see. No, you have also bent the Fermi level. Okay, yeah, then it is kind of good. Yes, correct. Okay. Yeah, this is correct. But your only one band has bent, the other one has not bent. Bending will be similar for both. Okay. Okay, yeah, I mean, okay, you want to try draw on the board? Okay, following the rules. Okay, you have to go rule by rule. Okay, why don't you try? Be careful here, huh? Very good. Yes. Very good. Yes. No, no, no. No, I think maybe I misread what you have drawn over there. No, follow the rules. Follow the rules, right? Rule number 1, you are correct. Okay. So after rule number 1, you are correct. Now let's do rule number 2, the easy one, right? Rule number 2 is the easy one. Where will be your bands? Yes. Okay. Correct. And the valence band? No, closer. It's a p-type material. You see? Right. You see, and then EV. Yes, correct. So far, so good. Yes. So here, where is the chi and where is the phi m? But chi is smaller and phi m is larger, right? So at this point, if phi m is this far, chi should be closer. That's the rule number 2, correct? Yeah. Then it cannot bend like this, because your conduction band has to be somewhere here. It is not different than the first picture we have drawn. No, 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 no. You want to draw it? Right? No, no, no. Bending is not going to be this direction. No, no. Somebody has to clear. Where is that? I kept it. Oh. Rules don't change based on p and n type material. What I told you is that, where is the chi? Chi's position with respect to phi m should remain the same, and phi is smaller. Yeah. No, EC doesn't go up that high. Okay. Okay. Yeah. No, 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 no. See. Okay. The relative, because I told you that the chi has to be smaller, right, compared to phi m. That's how it is. So this is how the bending is going to be. Practice drawing band diagrams. Okay. But you know the rules. Yeah. What is it? Phi s we don't care. We don't care about the phi s. We only care about the chi and the phi m at the interface. Make sense? Okay. Good. And now you see there is a Schottky barrier for the hole injection, because holes are going to go in the valence band, right? So if I wanted to make a ohmic contact for hole injection, what kind of a work function of a metal should I choose? I should, what is it? I didn't get it. What is it? No, no, no. Ferroelectric is not a metal at all. Ferroelectric is a different set of material. We are talking about metals, right? A smaller work function or lower work function. Like you saw in the previous thing, what did we choose for a n-type material? A smaller work function metal. Phi m is small. What should we do for a p-type material? I should simply choose a very large work function metal. Correct? For ohmic contact, because now you see the valence band has bent so much that the Fermi level is below the EV. For n type, I need the Fermi level to be above the conduction band. For p type, I need the Fermi level to be below the valence band, right? So therefore, a low work function metal is good to make an n type FET. A high work function metal is good for making a p type FET, right? And you can see by doing work function engineering without changing the 2D material, right, by just changing the metal, I can get an ohmic contact or a Schottky contact. Make sense? Any confusion you have, ask me. We have to, because you saw that in order for me to get to the IRDS roadmap, I need an ohmic contact in the first place, because if I don't start with the ohmic contact with the Schottky barrier, my contact starts with a larger number, right? At the end of the day, what is my objective? Is to reduce the contact resistance. And Schottky barrier is nothing like, as I told you, if you have a wall in front of you, if you are going somewhere, you have to cross that wall, you will be slowing down, correct? So there is no other option but to make an ohmic contact. But making an ohmic contact also requires engineering. Just taking a metal and putting it on the semiconductor is not going to give me an ohmic contact. I have to find the right metal with the right semiconductor, because I have to make sure that if I go over here, right, you see the Schottky barrier for n-type material is the phi m minus chi. So I know my electron affinity of the 2D material, so I have to choose my contact accordingly, right. Let us say for MOS2, this chi is 3.5. Okay, let me give you some number, and now let us do some more numerical stuff. Let us say chi is 3.5 eV for MOS2. Okay. So in order to get a ohmic contact, what work function of metal should I choose from this expression? What do I want? I want my phi SBN to be positive or negative? Positive. Positive will have a Schottky barrier. This is what we just spoke about, right? What did we say? This is a positive Schottky barrier. This is a negative Schottky barrier, correct? And that is an ohmic contact. The Schottky barrier height has to go away. If there is a barrier which is finite in height, then it is not an ohmic contact, right? You have to put the wall inside the ground so that you will be able to walk freely. Same concept, right? So you need to make sure your Schottky, not too big, and then you will be a hole, and then you will fall in that hole. That doesn't happen here. But you see, so you have to make sure that your phi SBN is negative, right? So if this is 3.5, your work function of the metal should be lower than 3.5, right? So that's why we choose metals like titanium, right, scandium. These all have bismuth. These all have work function less than 3 or 3.5, right? While palladium, let's say for example, right, the work function is generally 5.5 eV. Will I choose palladium for making an n-type contact? No. Makes sense? But exactly the other way around for p-type. For p-type, the barrier height was actually Eg, because there is a band gap minus phi m plus chi. It is just that the height of the Schottky barrier for the n and p adds up to the band gap, correct? That part is clear, right? So therefore, for a p-type material, I would like to have a larger work function metal, because you see the slope is actually exactly the other way around. Large work function, small work function metal takes me below 0, large work function metal takes me below 0 for p-type. So choosing the right metal becomes important to get ohmic contact for both N and P. This is established. It is material specific. Exactly, right? So now let me do a few more. So quiz is already happening. Lucky, I think we may not need to do the quiz on the last day. Quiz is already happening. Okay. So now I will give you two materials. Okay. One material, I really want to use a board. So can we get a better duster? A better duster would be nice. Yeah. Okay. So two scenarios. Okay. Material 1. Maybe I will use this. You want to move a little bit? You want to, oh, there is no seats on the other side. Oh, you can sit here. Yeah, here. You can sit here. Yeah. Okay. So material 1. Okay. Let's say this material is black phosphorus. This is a 2D material, okay. And then there's another material which is MOS2. This is material 2. Okay, this guy has a band gap of, let's say, 0.8 eV, and this is my MOS2, which has a band gap, monolayer MOS2 has a band gap of 1.8 eV. Okay, which material you think will be easier to make both N and P type contacts? I'm also going to give a few more information. Okay. The other information is I have choices for metal. I have some metal choices: titanium, nickel, gold, palladium. Titanium has a work function of 3. Let's put this, let's say 3.5, 4, 4.5, and let's say 5 eV. Okay. This is one information, and then I have drawn the band diagram for the black phosphorus and for MOS2. Okay. Let's say they are intrinsic. I have not doped them. Chi value I am also going to give you. Let's put it this way. So let me draw it with respect to the vacuum level. They are very much the same, and here is different, and let's say this is 2.5 eV. Okay. Let's put it 3.5 eV. I'm just making up some numbers. This is just a quiz. I'm just making it up, and this is 1.8 eV. This is also 3.5. Okay. Now, can you tell me for which material, which metal will you choose? Let me make a simpler problem. For which material, which metal will you choose for an N-type transistor and for a P-type transistor? You just have to mix and match, right? So let me, oh yes, that would be nice. Perfect. Think about those. There is a curve over there, right? Yes, यहाँ की रहने दीजिए. Then I can use it to clean the board. हाँ, काफी है. Good, good. This is good. So you have to populate this table. Okay. I want. Oh, अभी तो ये नहीं हो रहा है क्योंकि अभी पहुंचा है. Has to settle down a little bit. Okay. So black phosphorus, MOS2. उसको रखने दीजिए. ठीक है ठीक है ठीक है ठीक है, मैं लिख लेता हूँ. इट्स ओके. नहीं नहीं, ये फाइन. ठीक है ठीक है. टाइटेनियम, निकल, गोल्ड, पैलेडियम. बाकी सब दिख रहा है ना? ओके. सो BP, MOS2, N-type, P-type. Okay. You have to now populate this table. Which metal will go where? No, I told you. Schottky barrier has to be negative. Schottky barrier has to be negative. Choose the metal and populate this table. You also have to look at this, both. थोड़ा स्कोर लीजिए. Our job will be half done. नहीं नहीं, it's fine. Okay, let's do one by one. Black phosphorus and FET, correct? So I want a Schottky barrier which should be 0 or negative, right? So which metal should give me, huh? No, no, no. AU is going to give me difference. So this is going to, these are the phi m, right? So we will choose titanium, correct? So this should be a titanium contact. Oh, this is Chi. This is Chi. This is Chi. Because the other information, as I told you, is not that important, right? It is only determining, what is the band bending. But the Schottky barrier height is primarily determined by the difference of the Chi and the work function. That's where this thing is. You see, you do not need to know where the Fermi level is. In this formula, is there any Fermi level position? Band gap, information given, Chi, information given, phi m, information given, correct? So now you tell me, for MOS2, if I wanted to make an N type, which material should I choose? It should also be Ti. Make sense? It should also be titanium. And what about the P type material? If I want to make a black phosphorus P type, what is the sum of these two? This is the Eg, right? So this is 4.3. So I could do either gold or palladium. Make sense? So I could choose gold as well as palladium. But what about MOS2? You cannot do this because 3.5 plus 1.8 is 5.3. So really none of these materials will actually work because palladium is 5. No, it has to be even more than the sum. You see, that's why I am saying, look at this. Your phi m has to be more than Eg plus Chi, right? Then only you will get negative. So none of these metals are going to work, correct? So you see why it is so much difficult to make P type contacts to 2D materials. This is our next topic. You see, there has been a lot of challenge in the community of getting a good P type contact or a P type FET, because black phosphorus is there but it is very unstable. For our MOS2, WSC2, you see the challenge. Yes. So nickel you can use for N type, right? But if you use nickel, what will be the Schottky barrier for N type? You see, phi m is 4 and Chi is 3.5. So 0.5, it's positive. So I cannot use a positive number. Then it will be a Schottky barrier. So nickel will be a Schottky barrier contact. You may actually go to something like bismuth, which is 3. That is a good one. Or antimony, correct? Yeah, minus 0.5, even better, right? I mean, you can probably go to something like platinum and maybe get to 5.5 EV. Okay, then you might be able to make a P type contact. You see, right? So then platinum could come here, correct? So you see, just by doing metal work function engineering alone is not good enough. It also has to come along with what is the electron affinity of the material, what is the band gap of the material, and a smaller band gap material is always easy to make contact with. A larger band gap material is very difficult because you do not have that big span of metal work function. Metals are just only these, right? You can take the periodic table and find how many metals are there. There are some compound metals. You can engineer metallic compounds, right? But not everything is going to be easily integrable with the technology, right? So you see, there are challenges with contacts. Okay. Yeah. No. It can change. I mean, for a material it is given, okay, but it will change based on MOS2 versus WSC2 versus WS2. This number can be varying between anywhere from 3 EV to 4 EV. But typical numbers are these. Yeah, typical numbers are these. Yeah, correct, exactly. This part is clear, okay. But now I will show you that this is an even severe problem, okay. So you see, by changing the metal work function, I can kind of find out N and P only if this was the experimental plot, that I change the work function by 1 eV, Schottky barrier changes by 1 eV. That's what this relation tells me. This does not happen in reality. If you do the experiment, you will find that the slope is actually worse, which means that I can change the work function of the metal by 1 eV, but the Schottky barrier height changes only by 0.2 eV. Then I am in even deeper problem, right? If only a part of the work function goes in here, and if this factor is 0.1, now I am looking for a material which is a work function of 10 eV to get a negative Schottky barrier height, right? If the factor is less than 1, I do not get the full benefit of my metal work function, right? And this is something that we see. Alpha equals to 1 is the ideal case, but in experiments it is never ideal. For silicon, this number is 0.27, okay, and for MOS2 it is even worse, it is 0.1, okay. So therefore, and this happens because of something called metal induced gap states. We are not going to go into there, it is even much digging much deeper, let us not go there. But whenever you put metal on top of a 2D material, because of many reasons, could be the damage due to the evaporation, or exchange of electrons or holes between the metal and the semiconductor, there are some gap states, okay, and this gap state pins the Fermi level. This is called the Fermi level pinning, okay. And because of the Fermi level pinning, no matter, even if you choose platinum, which we thought of giving us p type characteristics, you see where is the Fermi level of platinum with respect to MOS2? It is very similar to where scandium and titanium is. So I can change the work function by 1 eV, but reality it only changes by 0.2, making a p type FET almost impossible for 2D material, for MOS2, right. So this is called Fermi level pinning, because just by changing the work function, I am not being able to change the Fermi level of the metal with respect to the semiconductor, which we just draw, okay. That is a severe problem, you see. So you only get NFET even with platinum contact, right. The same thing happens for tungsten selenide. In tungsten selenide, this pinning happens mid gap. So you get kind of little bit N, little bit P, and it becomes ambipolar, okay. But both branches are pretty low in the current because they are going through a Schottky barrier. Better for black phosphorus, but black phosphorus, the pinning is more close to the valence band. So you can get an easy P FET, but you cannot get a nice N FET, okay. So this is another level of problem with the 2D materials, this Fermi level pinning, okay, which kind of defies our textbook understanding. So therefore it becomes even severe, right, because ultimately we have to make a ohmic contact, right. So these are a lot of the papers that we have published, and you see that now we have understood that we cannot get rid of the Schottky barrier. We have to live with Schottky barrier and somehow still get a better injection, right. So there is a wall between you and your Sangam. You have to cross, you can jump over the wall, or you can make the wall very thin, and if you are an electron, then you can tunnel through, So we human beings cannot take the advantage of a thinner wall, but the electrons can, right, because they are quantum mechanical particles. So therefore if I cannot make it short, I have to make it very thin, right, and then I will be able to allow injection, and that I can do because this width of the Schottky barrier depends upon the doping, okay. This is an old formula, you have probably seen it in p-n junction diodes and metal semiconductor contact. I am not going to derive it, okay, because that will be a lecture in itself, but you see that it depends inversely on the carrier concentration. So you have too much of carriers, then the Schottky barrier width becomes very small, right. This is why in silicon, if you go back and see the actual silicon device structure, underneath the contact they are heavily doped, N++ for an N type MOSFET, P++ for a P type MOSFET, because even for silicon we saw that this is Fermi level pinning, Schottky barrier is there, but yet in silicon you can make very good contact because you can degenerately dope it and make the Schottky barrier so thin that in spite of its presence it is almost non-existent, because if the Schottky barrier becomes almost close to 0, then the electrons can tunnel through, right. That is the wonder of quantum mechanics, right. So, use that quantum mechanics then to mitigate this contact resistance channel trouble by degenerately doping this. This is not available for the 2D materials, because how do you dope silicon? By ion implantation, right. But if you do ion implantation on a monolayer, forget about any doping, it will not even survive, right. So, substitutional doping is very difficult for 2D material. So, you can only do substitutional doping during growth, right. During the growth you can introduce doping, but during the growth if you introduce, will you be able to selectively dope only the contacts? No, the entire material is then doped. I do not want that, right. I only want it to be in the contact area. So, that today still remains a challenge. It is a good PhD problem. Okay. We are still working on this thing. How do we get to degenerate doping in selective areas? Because if I dope the entire channel selective, degenerately, it is a metal. Who wants to use a metal for a semiconductor as a channel? You see, right? You have to selectively dope underneath the contact. That will give you your best contact resistance. Make sense? Okay. Now, there are different ways we can do that. Contact is, so what we spoke about so far is still very textbook. Okay. Reality is very different, because when you are trying to make contacts, right, the nature of the interface can change. For example, if you put molybdenum, okay, it will form a covalent bonding with the molybdenum sulfide underneath. The same with titanium, okay, but with gold it will remain van der Waals. Gold will not form a bond, right. Silver, for example, will not form a bond, but silver is a metal which can also intercalate. If it is a multi-layer TMD, it can also go between the layers, because it is a very mobile ion. Okay. Silver can do that. So, just the work function of the metal does not determine where the Fermi level is going to be, also depends upon the nature of the chemical interface, right, which is not there in the discussion that we just did, right. And you see that what we found is, if you do covalent bonding, in case of molybdenum the contact resistance is low, but a similar covalent bonding with Ti, the contact resistance is high, right. Gold, for example, van der Waals contacts, the contact resistance is low. So, there is also a lot of missing understanding in the field right now, that whether you want a covalent bonding with the metal that you are putting on top, or you want it to be a van der Waals. Okay. Still an to some extent an unanswered question in the field. Okay. Metal 2D interfaces and metal semiconductor interfaces are very complex. Okay. There are lots going on, because when you are depositing, whether you are depositing using sputtering or e-beam evaporation or thermal evaporation, it all matters, because the energy with which these metal particle goes and bombards your 2D surface, that is also going to change the contact resistance, right. And even if you stay with the same tool, let us say you are using the electron beam lithography, or e-beam evaporation, based on how fast you do the deposition or what is your vacuum condition of the tool, that will also impact your contact resistance, you see. So, therefore, contacts remain a big challenge in the field, and so much fundamental understanding still needs to be developed. Okay. But even with that, there has been a lot of good work actually. This is a work from Cambridge, where they were able to kind of do this selective doping, but in a very interesting manner. They were able to do phase engineering, because MOS2 exists in both 2H phase, which is semiconductor, and 1T phase, which is a metal. So, at the end of the day, you want a metal as a contact, right. So, this group actually showed that just by treating the contact area with some chemical, you can transform it into 1T. So, now you have a metal contact atomistically clean to a semiconducting material. This is like a selective area doping that we were talking about, but now instead of doping, they have literally converted into a full metal, and they showed that okay, the contact resistance could be low. You see, the number is not bad. Okay, it is not 50 ohm micrometer, but it is still like 480 ohm micrometer, right. So, that is one approach. More recent approaches have shown that if you use, let us say for example, antimony, Okay. The antimony contacts can give you a contact resistance down to 42 ohm micrometer. That is kind of reaching our target. So, for MOS2 N type antimony contacts appears to be the killer. Okay. And you can see that it has happened after so long. It took almost like 12 years to figure out how to get to very high performance. And you can see what happens with titanium, nickel, bismuth. You see, as you go to lower and lower work function metal, you get to better performance, right? It kind of follows what we were just discussing over there. But antimony kills it, because antimony has, not only is the other thing that I did not mention also about the epitaxy. Okay, what was found is that antimony, metals generally have very small grain sizes. So generally we don't talk about the epitaxy of metal, right? But antimony on MOS2 actually have bigger grain sizes. Okay, and that's why we call, it's more epitaxial contact, and that also gives lower contact resistance. Okay. There is also, we have another study where we have also looked into the strain, because when you put a metal on 2D material, nickel will create a lot of stress, while if you put something like gold, it will not stress the material. So stress and strain, the mechanics of the contact also impacts contact resistance. Changes mobility, it changes the band gap, it has even more impact on the contact, right? Yeah. Yes. Yeah, it's a padding, just because of the fact of two things, that antimony may not be very, because practically you have to land your probes, okay, and antimony you may scratch it. It's not very ductile. So gold is actually good to have a capping layer. That doesn't matter actually. It's all based on the lithography. So you can use 10 nanometer, 20 nanometer. You could literally use even nickel, titanium, anything as a capping layer. Okay, that is all like based on your particular need and how good is your probe station is. Because as long as your contact is more than 3 to 5 nanometers, that's your contact. The gold does not influence your contact because it's too far, as we saw, right? It does not impact anything. So you can really cap it with whatever is available in your evaporator. Most often than not, it is all about what do you have in your evaporators, and you put that metal and what works for you. Okay. All good up to this point. And then these are some of our own data. This is not published yet. We are trying to publish this, and you can see that even in our devices we can now reach very high performance. Let me not go into too much detail into this, because you guys will be a little bit lost. There are other things which are also important for 2D FETs. But as I told you that all these studies which achieved very low contact resistance achieved it for a big contact, right? We are going back to our drawing room and now asking the question, okay, I choose antimony, right, or I choose gold. Both are actually very good contact, but what happens when I make the contact very small, because that is still an unanswered question. Okay, because one may actually show better scaling compared to the other, because at the end of the day I have to make the contact small and then achieve 50 ohm micrometers. So the number that we have achieved is for big contacts, right, and we just have seen that the big contacts is not good. So what we found out, lot of device data, don't get overwhelmed by that, but we found is that when you make the contact very small, you see over here, right, from 500 nanometer contact to 30 nanometer, that's what we need for our technology, right. You see that the contact resistance goes high, right. Smaller contacts have larger resistance compared to the bigger contacts, right. And this is where we try to show that this is the first time some of this work has been done. We found that if you use a mono layer, then this contact resistance is much higher, while if you go to bilayer or tri-layer, you see the contact resistance is lower. Okay, why? Because bilayer has a smaller band gap, which makes making contact easier. Okay, but the rule for the IRDS is that your channel material has to be less than 2 nanometer thickness. So now you can say, okay, why don't you go to 10 layers, right? If I go to 10 layers, then the thickness of the material becomes 6.5 nanometer, because each layer is like 0.65 nanometer. Then I should not use it, because silicon is already 6 nanometer. So the IRDS requirement is your channel has to be thinner than 2 nanometer, which means it has to be 2 or 3 layers. That is still allowable. So showed that in a 3 layer you kind of achieve, but still the contact resistance is a little bit higher. You see, it is not like 50 ohm micrometer. So the challenge of getting to 50 ohm micrometer in a scaled contact still remains. Okay, these are some of the other studies. We don't care. A lot of benchmarking. Don't worry about these things. This is just from the paper that we have written. Just to show, I think you can look into this column. This is what we have been discussing. This is in kilo ohm micrometer units. So just multiply by 1000, and you can see where does the field stand right now. This is the one that I was talking about, correct? 40 ohm, 42, but look at the contact length, red. We have to make sure that everything is green, right? So that has not happened. Whoever has achieved, lower contact has achieved it for a bigger contact, right? And you can see for some of our contacts, right, which is very scaled, right, we are quite far, right? For 3 layers, that's what I am saying. For mono layer it is 2.14. For mono layer we are like 930 ohm micrometer, but still quite far from 50 ohm micrometer, right? So that still remains a challenge in the field, and if you can solve it, you will get a Nature paper. Okay. With that, I will summarize what we have learned. So contacts are absolutely important, and they are even more important for a scale device, right? Second, contact resistance increases as I scale my contact, which is counterintuitive to what happens to the channel, right? 2D metal contacts on top of that suffers from this Fermi level pinning. So just metal work function engineering cannot rescue me to get to an ohmic contact. Third point. Fourth is gold, bismuth, antimony appears to be promising because they give me low contact resistance for MOS or N type. And then we need degenerate doping underneath the contact in order to achieve, because we cannot get rid of the Schottky barrier, we have to thin it down. And in order to thin the Schottky barrier, I need degenerate doping, and this is an open field. Okay, nobody has looked into that. We found that few layer MOS2 can alleviate the contact problem a little bit, right? And the target value for the contact resistance still remains at 50 ohm micrometer. Okay. With that, I will end this lecture here.